I'd like to start Chapter 5 in this segment. And so, Chapter 5 is we're going to take what we learned in Chapter 4 and we're going to be applying it to a lot of different situations. So, really, there's kind of not new physics in Chapter 5. It's really just learning to apply the physics that we learned in Chapter 4. And so, in Chapter 4, we approached Newton's second law as sort of a cause and effect relationship. Force is the cause, acceleration is the effect. And in that case, we wrote Newton's second law as A equals F net over M. Now, in this chapter, we're going to kind of rearrange that, and we're going to be mostly approaching Newton's second law, starting here, which I acknowledge is exactly the same as if we isolated A, but it's just sort of a different way of visualizing it. In other words, what do net forces do? They cause mass times accelerations. And so this is sort of what we're going to be, Chapter 5 is all about learning how to apply this equation. We're going to start off with maybe the simplest way to apply this equation, and that is objects that are in equilibrium. What does equilibrium mean? Well, in the case of physics, equilibrium means that the object is not accelerating. And so if we are in an equilibrium situation and the acceleration is 0, then this whole thing equals 0. And so another way to think about equilibrium is that an object is in equilibrium when the net force is equal to 0. Now, something that can be a little bit tricky about these problems and about understanding Newton's second law is notice this is not force equals mass times acceleration. It's net force equals mass times acceleration. So just because something has an acceleration of 0, we are not to assume that that means that there are no forces acting on the object. We are to assume that the net force is 0, which is different from there being no forces. For example, if we looked at any one of these individuals, none of them is accelerating. So they are all in equilibrium, which means that the net force on every one of these individuals is 0. But if we were to take any one of these individuals, I don't know, say one of these people that is way down here in the middle of the stack, does that person have forces acting on them? Oh yeah, big forces, right? There's probably a lot of forces acting on somebody that's down here in the middle of the stack. However, all of those forces cancel, causing that person to not accelerate. Now, much like we did in the projectile motion section, one of our number one problem-solving strategies here is to break down the x and the y components. And so we're going to solve this problem in the x direction and in the y direction. That's not the only way to apply this equation, but that's the strategy that in general we are going to apply to this situation. And so what this ends up looking like is we have one vector equation here. This ends up looking like one equation for the x and one equation for the y, which I have written out here on the PowerPoint. The sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. Our book uses the convention that it calls F net here for our vector sum equation. And then they use this symbol here in the x and the y. But really, they mean the same thing, right? This symbol here means add up all of the forces in the x direction. So this means add up all of the forces in the x direction. That's what this means too. This means take the total force. Okay, so a little bit of a subtle detail there, but that's just what the book does. Essentially, saying this and F net are the same thing. Okay, now if something's not accelerating, we know that that could either be constant motion in a straight line, so constant speed in a straight line, or it could be at rest. Both of those have an acceleration of 0. And so we're going to distinguish here. We're going to say static equilibrium is when an object has an acceleration of 0 and is at rest. And we're going to say that dynamic equilibrium is an object that has an acceleration of 0 and is moving in a straight line at a constant speed. But in both cases, a sub x and a sub y are 0. Let's do a really quick example. So here's this ring. We're viewing it from above. It's pulled on by 3 forces. The ring is not moving, so its acceleration is 0. How big is this force F? Now, I didn't give you a number for theta, right? So your answer will end up having a theta in it, unless you think it's 20. Why don't you pause the video, see if you can't figure out. I'll see you on the other side. Okay, so in this case, what we need to do is we need to approach this from an x and a y perspective. Right? We've got our ring here, we've got these two forces here, and we've got this one force here. And these are both 10 newtons. So this is going to be our first chance to use our problem-solving strategy for forces, where we break things down into the x and the y components. Since F is in the y direction, I'm going to start with the y direction. The sum of the forces in the y direction equals 0. This is an equilibrium problem. Well, we need to define a coordinate system. If I'm saying I'm in the y direction, I better tell the world what I mean by the y direction. We'll use a standard coordinate system where positive y is up. Notice that this F is entirely in the y direction. However, these two forces are not. These two forces are not in the y direction, and so we need to break them down and find their components. I'm going to redraw this just a little bit to give myself a bit more room here. And that's 10 newtons there. Okay, so I'm going to break this down then. I'm going to make this into my x and my y components. So what I need to do is find the components of this 10 newtons, specifically the y component of this 10 newtons, which I have labeled B on my triangle. So in that case, B, notice, is opposite, and so I would write that B is equal to 10 newtons times the opposite is sine of theta. So 10 newtons sine of theta. Now I'm ready to apply this equation right here. So the sum of the forces in the y direction equals 0. What forces do I have? Well, I have a positive B, and notice by symmetry, the y component of this 10 newtons is the same. So in other words, I have 10 newtons times the sine of theta, one of those. I have another 10 newtons plus the sine times the sine of theta. And I have a negative F equals 0. Why is it a negative F? Well, because it's pointing down. It's pointing in the negative x direction, whereas it's pointing in the negative y direction, whereas both of these are pointing in the positive y direction. Solving this equation for F, 20 newtons times the sine of theta. Now, it's entirely possible that you're feeling comfortable with vectors and components. It's entirely possible that you were able to just kind of think your way through this, just kind of without having to draw a picture and do all this algebra. Totally fine. If you were able to, then you did all this algebra in your head, right? You still did this. It's just that you did it in your head. And I guess I would encourage you to practice this algebra on the simpler problems so that when we get to the trickier problems, that you can't just kind of reason your way through, that you've got those skills and that you've established those skills on the easier problems. Okay, great, there it is. Winner, winner, chicken